Imagine you're given a problem. Not a hard problem, an impossible one. A calculation so vast, so deeply layered, that if every computer ever built by human hands worked on it simultaneously, without stopping, without error, from the moment the first stars formed in this universe, they still wouldn't be close to finishing. Not even close. Now, imagine someone hands you a chip smaller than your palm, and it solves that same problem in under 5 minutes. That's not science fiction. That happened in December 2024. Google announced a quantum processor called Willow, and what it didn't just break records, it broke something far more fundamental, our understanding of where computation actually happens. Because when physicists looked at the numbers, really looked at them, they couldn't account for where the processing power was coming from. Not from this universe anyway. December 9th, 2024, Google's quantum AI team publishes a paper in the journal Nature. It's titled with the kind of quiet academic confidence that hides something extraordinary underneath. The subject, a new quantum processor called Willow, and its performance on what researchers call a random circuit sampling benchmark, a specific type of computational task designed to stress test quantum systems against their classical counterparts. The result, written in precise academic language, lands like a thunderclap. Willow completed this benchmark in under 5 minutes. The best classical supercomputer on Earth, a machine that fills entire rooms, burns enough electricity to power small towns, cooled by systems more complex than most aircraft, would need 10 septillion years to do the same thing. Let that number breathe for a moment. 10 septillion. That's a 10 followed by 24 zeros. Our universe is approximately 13.8 billion years old. 10 septillion years is roughly 1 trillion times longer than the universe has existed. It's a number so large that it stops being a number and starts being a philosophical statement, a declaration that certain things are simply beyond classical reach. And Willow did it in the time it takes to brew a pot of coffee. Now, quantum computers have claimed supremacy before. In 2019, Google's earlier chip, Sycamore, made similar headlines. But Sycamore's advantage, while real, was contested. Critics pointed out that classical algorithms could be improved to narrow the gap. The margin felt like a sprint, impressive, but challengeable. Willow is different in kind, not just degree. The performance gap between Willow and classical machines has grown so astronomically large that no foreseeable improvement to classical computing could close it. We're not talking about being faster. We're talking about operating in a fundamentally different category of reality. And that's where the story gets strange. To understand why physicists started talking about parallel universes in the same breath as circuit boards and laboratory benchmarks, we need to step back and ask a question that sounds almost childishly simple. What is a quantum computer actually doing? A classical computer thinks in bits. Each bit is a 1 or a 0, a light switch, either on or off. Everything your phone does, every email, every video, every word processor calculation is ultimately a sequence of 1s and 0s moving through logic gates at incredible speed. A quantum computer thinks in qubits, and a qubit can be both 1 and 0 simultaneously, a state called superposition. This isn't a metaphor or a simplification. It is literally, physically, mathematically the case that a qubit exists in multiple states at once until you observe it. At that point, it collapses into a single answer. This is strange, but it gets stranger. When you scale qubits up and link them together through a process called entanglement, the system doesn't just get twice as powerful with each new qubit, it gets exponentially more powerful. 2 qubits can hold 4 states simultaneously. 3 qubits hold 8. 10 qubits hold over 1,000. By the time you reach Willow's scale of 105 qubits, the number of simultaneous states the system can theoretically process is larger than the number of atoms in the observable universe. Larger than the number of atoms in the observable universe. So, here is the question that has been quietly haunting quantum physicists for decades, and that Willow has now forced into the mainstream conversation. Where is all that computation physically happening? In a classical computer, the answer is obvious. The calculation happens in the processor in the silicon, in this room, on this planet, in this universe. The computation is local, physical, traceable. But in a quantum computer operating at Willow's scale, the number of simultaneous computations being performed exceeds what could possibly be hosted within the physical matter of the chip itself, or, some physicists argue, within the observable universe at all. This is not a fringe observation. This was stated directly and publicly by one of the founding fathers of quantum computing himself. David Deutsch, the Oxford physicist who first proposed the theoretical model of a quantum computer in 1985, has argued for decades that the only coherent explanation for how quantum computers work is that they are, in a very literal sense, performing calculations across multiple branches of reality simultaneously. His framework is called the many worlds interpretation of quantum mechanics. And with Willow, it just became very difficult to dismiss. The many worlds interpretation, sometimes called the Everett interpretation, after physicist Hugh Everett III, who first formalized it in 1957, proposes something radical but mathematically consistent. Every quantum event, every point at which a particle could go one way or another, doesn't result in a single outcome. Instead, reality branches. Both outcomes happen. The universe splits into versions of itself where each possibility is realized. There is no collapse, no random selection, no cosmic dice roll. Everything that can happen does happen, just in different branches of an ever-expanding infinite multiverse. Most people encounter this idea as science fiction, but in the physics community, the many worlds interpretation is one of the most seriously debated frameworks for understanding quantum mechanics. It's not a fringe theory. It is arguably the most mathematically natural reading of the Schrödinger equation, the core equation governing quantum behavior. David Deutsch took this seriously enough to build a career around it, and his core argument, stated plainly, is this. When a quantum computer performs a calculation, it is performing that calculation across many parallel worlds simultaneously. The answer arrives in our world, but the work was distributed across the multiverse. For most of computing history, this was an elegant philosophical position. Interesting, but not something you could point to directly. Quantum computers existed, but at small enough scales, you could tell yourself the explanation was simply the mathematics of superposition contained within a single system. Willow changes that conversation, because when Google's team reports that this chip performed a computation that would take classical systems 10 septillion years, a number that exceeds the lifespan of the universe by incomprehensible orders of magnitude, and did it in 5 minutes on a chip with 105 physical qubits sitting in a refrigerator in California, the honest scientific question becomes, where did the computational resources come from? Not rhetorically, literally, physically, where? Dr. Amara Okonkwo, a quantum systems researcher whose work bridges computational theory and experimental physics, described the Willow results to colleagues in terms that were striking for their candor. The benchmark result isn't just about speed, she noted during a panel discussion on quantum advantage in early 2025. It's about the fundamental question of where computation lives. At this scale, we're being forced to ask whether our models of physical reality are adequate to explain what we're building. And the uncomfortable answer might be that they're not. That discomfort is shared across the field, though expressed with varying degrees of caution. Professor Liang Chen, a theoretical physicist at MIT who specializes in quantum information theory, has written extensively about the interpretational gap, the space between what quantum computers demonstrably do and what our current physical models can cleanly explain. The many worlds framework isn't something physicists invoke lightly, Chen noted, but when you're looking at computational capacity that scales beyond what classical physical systems could theoretically provide, you have to start taking seriously the possibility that the computation is genuinely distributed, not metaphorically, but ontologically, across configurations of reality we don't have direct access to. The language is careful, measured, but the implication is extraordinary. And then there's the perspective that comes from Google's own team. In the official blog post accompanying the Nature publication, Google's researchers reference the many worlds interpretation directly, not as speculation, but as a legitimate framework for understanding what their chip is doing. They describe the computation as drawing on resources that, in Deutsch's framework, would correspond to parallel computational branches, parallel universes in the most technically precise sense of that phrase. This is a company known for careful, PR-conscious communication. They don't invoke parallel universes casually. Let's be precise about what is and isn't being claimed here, because this is where the science needs to stay tethered. No physicist is suggesting that Google's lab has a window into a parallel universe. No one is claiming they've received a signal from an alternate Earth, or that there's some kind of portal or wormhole involved. What is being discussed, seriously, rigorously, by credentialed physicists is something more subtle and, in its own way, more profound. In quantum mechanics, the state of a system is described by what's called a wave function. This mathematical object encodes all the possible configurations a quantum system could be in. When a quantum computer operates, it manipulates this wave function across all its possible configurations simultaneously. In the Copenhagen interpretation, the traditional framework most of us learn first, you say the quantum system is in superposition and leave it at that. The wave function is a mathematical tool, not a description of physical reality. But in the many worlds interpretation, the wave function is physical reality. Each branch of that wave function represents an actual existing configuration of the universe. And when a quantum computer processes information, it's doing real computation in each of those branches, real work distributed across real versions of reality. The answer that arrives in our branch is the result of that distributed labor. Think of it this way. Imagine you have a question so complex that answering it would require consulting every book ever written. You can't do it alone. But what if, at the moment you ask the question, thousands of identical copies of you in thousands of identical libraries each began working on a different section, and then somehow, all that work folded back into your single answer? That's a rough metaphor for what quantum computation may be doing across the fabric of reality. The Willow chip's performance forces this question out of the seminar room and into the laboratory, because the numbers don't work any other way. If you try to account for Willow's computational output using only the resources available in one classical configuration of matter, one universe, the books don't balance. The processing power isn't there. Something is making up the difference. And the most mathematically coherent explanation currently on the table is that the computation is genuinely happening across multiple branches of a many worlds reality. Parallel universes lending their computational capacity to a tiny, cold chip in Mountain View, California. Here's something that got less attention than the septillion-year headline, but may actually be more significant in the long run. Willow didn't just demonstrate raw speed. It demonstrated something that quantum computing researchers have been chasing for years without success: reliable scaling, error correction. Quantum systems are fragile. Qubits are exquisitely sensitive to their environment: heat, vibration, stray electromagnetic fields. Any of these can introduce errors into a computation, and those errors compound rapidly. This is called decoherence, and it's been one of the central unsolved challenges of building practical quantum computers. Previous quantum systems faced a brutal trade-off. Add more qubits to increase power, and you increase the error rate. The noise grows with the system. This meant that quantum computers were stuck in a kind of valley, powerful in theory, limited in practice. Willow broke that pattern. Google's team demonstrated that as they added more qubits to the Willow system, the error rate went down, not up. Down. This is called below-threshold error correction, and achieving it is one of the holy grails of the field. It means that Willow's architecture can, in principle, be scaled up. More qubits, more power, fewer errors, without the system collapsing under its own quantum fragility. The implications here are difficult to overstate. Dr. Priya Mehta, a quantum error correction specialist whose research has focused on topological qubit stabilization, described the error correction result as the more technically surprising of the two achievements. The benchmark performance is astonishing, but benchmarks can be debated, she observed in a post-publication commentary. The error correction scaling behavior is unambiguous. It tells us that the engineering path toward fault-tolerant quantum computing is real. We're not talking about a physics demonstration anymore. We're talking about a technology trajectory. That trajectory points toward a world where quantum computers aren't just curiosities for academic benchmarks. They're tools, practical, powerful tools, capable of solving problems in chemistry, materials science, cryptography, and medicine that no classical computer could ever approach. But sitting underneath all of that practical promise is the deeper, stranger truth. We may be building tools that work precisely because they reach beyond the boundaries of our known universe. Let's sit with that for a moment. If the many worlds interpretation is correct, and a growing number of serious physicists believe it is the most internally consistent framework we have, then parallel universes aren't just a metaphor or a thought experiment. They're physical, they exist, and they're not somewhere impossibly remote. They're adjacent to this one in a mathematical sense that is more intimate than any distance in space. And if Willow is genuinely drawing computational resources from those branches, if the work is genuinely distributed across parallel configurations of reality, then we've done something remarkable without fully understanding what we've done. We've built a device that operates across the multiverse, not by understanding the multiverse, not by mapping it or communicating with it in any meaningful directional sense, but by exploiting the mathematical structure of quantum reality in a way that makes parallel computational branches do useful work for us. It's a bit like early humanity using fire without understanding combustion chemistry. The mechanism was real and powerful long before we had the framework to explain it. The philosophical vertigo here is genuine and worth acknowledging. If the universe branches at every quantum event, and every quantum event means every interaction at the subatomic level, which is to say, every moment in every atom of everything, then there are versions of this universe beyond counting. Versions where different choices were made, where different particles went different ways, where history unfolded along different lines. Most of those branches will never touch ours in any detectable way. The quantum coherence that would allow interference between branches breaks down almost instantly at the scales we can observe directly. But inside a quantum computer, cooled to temperatures colder than deep space, isolated from environmental noise with extraordinary precision, operating in carefully maintained quantum coherence, the branches can be made to interfere with each other constructively. And that constructive interference is computation. Real computation distributed across real parallel branches of a real multiverse. Willow is, at least according to this framework, the most literal multiverse interfacing device ever built. This is the part where good science requires us to slow down and apply some intellectual honesty. Not everyone accepts the many worlds interpretation, and some physicists who study quantum computing closely are skeptical that Willow's results require invoking parallel universes at all. The Copenhagen interpretation, the view that quantum superposition is simply a mathematical description of probabilities, not a physical description of parallel worlds, can accommodate quantum computation without invoking the multiverse. In this view, a quantum computer is extraordinarily clever at manipulating probability amplitudes, but it isn't literally computing in other universes. It's computing here, using the mathematical structure of quantum interference. Proponents of this view would argue that the "where is the computation happening" question is a category error. That asking where a probability lives is like asking where a dream is stored. Dr. Jonathan Harfield, a quantum information theorist at Caltech who leans toward the Copenhagen framework, has noted that the many worlds framing, while philosophically interesting, doesn't add predictive power. The many worlds interpretation and Copenhagen give identical predictions for every experiment we can currently run, he has written. Willow's results are extraordinary, but they don't distinguish between the interpretations. What they do is raise the stakes of the interpretational debate. because the answers matter more when the technology is real. This is the key point. The debate between interpretations of quantum mechanics has been running since the 1920s. It hasn't been resolved because, experimentally, the interpretations are indistinguishable. What Willow does is make the debate feel urgent in a way it never quite did before. Because if we're going to build machines that operate at this scale, machines that could eventually reshape chemistry, medicine, cryptography, and material science, we probably want to understand, at the deepest level we can reach, what those machines are actually doing. There's something quietly moving about this moment in science, if you step back far enough to see it whole. For most of human history, the universe was something we looked at. We developed our eyes, and then our telescopes, our radio dishes, and our space probes, our gravitational wave detectors, and our neutrino observatories. We got better and better at watching the cosmos, at receiving the universe's signals and making sense of them. Willow represents something different, not observation, interaction. If the many worlds framework is correct, we've built a device that doesn't just receive information about reality. It operates across the structure of reality itself, leveraging the branching architecture of the quantum multiverse to do useful computational work. We didn't do this on purpose, exactly. We built toward performance, we chased error correction and qubit coherence and benchmark results. But in doing so, we may have stumbled into contact with the deepest feature of how the universe is structured, not by looking at it from the outside, but by building something that works precisely because it reaches in. David Deutsch has said that the most important thing about quantum computers isn't what they compute, it's what they prove. They prove that the universe has a computational structure that goes beyond what any single classical reality could support. And if that's true, then the universe is both stranger and richer than the version of it most of us carry around in our heads. There's a tendency, when confronted with ideas like the multiverse, to feel something like vertigo, like the ground shifted, like the thing you thought of as everything just became a small corner of something immeasurably larger. But here's another way to sit with it. Every universe in that vast branching structure, if it exists, presumably runs on the same physics. The same quantum mechanics that makes your heartbeat possible, that keeps atoms from collapsing, that drives the chemistry of thought in your brain. The branches are different histories, different outcomes, but they're made of the same stuff. We're not alone in the universe in the way we usually mean when we ask that question. But we might not be alone in the cosmos either. Separated not by light years, but by quantum branching points, adjacent in a mathematical space we're only just beginning to explore. And our first real tool for reaching into that space is a chip the size of your thumbnail, cooled to a fraction of a degree above absolute zero, humming quietly in a laboratory. December 2024 will probably be remembered as a milestone year in the history of computing, but it might also be remembered as the year that a specific boundary began to blur, the one we'd always assumed existed between here and everywhere else. Willow didn't crack open the multiverse. It didn't send a message to a parallel Earth or receive one back. It didn't prove the many worlds. Willow's interpretation in any final, definitive sense. The debate continues, the mystery remains, but it did something that might matter just as much. It made the question undeniable. For decades, the many worlds interpretation was philosophy as much as physics. Beautiful, strange, but ultimately untestable and easy to set aside. Now there's a chip, a real device, a physical thing that performs computations no single universe of classical matter could support. And the honest scientific response to that, the response that follows where the data leads rather than where comfort points, is to take seriously the possibility that our universe isn't the totality of what exists, that it's a branch, one extraordinary, improbable, staggeringly beautiful branch of something far larger. We are a species that spent millennia believing we lived at the center of everything. The sun moved around us. The stars were decorations on a ceiling. The Earth was the stage, and we were the main event. Then came Copernicus, then Hubble. Then the discovery that our galaxy is one of perhaps 2 trillion in the observable universe alone. Each time the stage got bigger, and each time, rather than diminishing us, the expansion made the fact of our existence feel more remarkable, not less. Because here we are, in this improbable corner of reality, building machines that think in quantum superposition, touching the hem of the multiverse, asking questions that our universe may not be large enough to fully answer. That is what Willow is at its deepest level, not just a faster computer, a question in physical form. Where does computation live? Where does reality end? How many versions of this moment exist right now, branching from this single instant, unreachable but real? We don't know. And that not knowing is where all the best science begins. The universe, it turns out, is still just getting started, and so are we. If questions like this, questions that sit right at the edge of what we can know and what we can barely imagine, if those questions pull at something in you the way they pull at us, then you're in the right place. Subscribe if you haven't already. New discoveries don't wait for anyone, and the ones ahead of us are going to be extraordinary. Until next time, keep looking up, keep asking harder questions, and remember, every answer we find just reveals how much larger the universe really is.